In this video, we're going to look at definition of a derivative and how to use it to find the derivative of a function. So the formula for finding the derivative is equal to f prime of x, which is notation for the derivative function, is equal to the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. And here I have an example of a function. F of x is equal to negative 3x plus 4. And f of x plus h of that function is equal to negative 3 times x plus h plus 4. So you need to put an x plus h in everywhere there's an x in the function to get f of x plus h. And we're going to need to use that to use this formula. So in this first example, I want to use the general derivative formula, which means that we're going to find the general derivative and then plug in a value. And in this case, I want to find f prime of 2. So we're going to take the general derivative, plug in 2 at the end, and get an answer. And that's going to tell us the rate of change of this function at the value of 2. So we're going to use our formula, the limit as h approaches 0 of f of x plus h, which is x plus h squared minus 6 of x plus h minus f of x, which is x squared minus 6x, all divided by h. And now we need to simplify. So we're going to multiply all the terms out, distribute all our negatives, and then simplify this function, this limit. H goes to 0, and then x plus h squared gives us x squared plus 2xh plus h squared minus 6x minus 6h minus x squared, I'm going to distribute the negative here, plus 6x, all divided by h. And now we're going to take a look at the terms that cancel. So here we can see that we have a positive x squared and a negative x squared, and we have a positive 6x, and a negative 6x. And now I'm going to rewrite all of the terms that we have left. So we have the limit as h goes to 0 of 2xh plus h squared minus 6h, all divided by h. And now we want to factor an h out of the top. So we have a limit as h goes to 0 of h times 2x plus h minus 6, all divided by h. So now we have an h on top and an h on bottom that we can cancel. So I'm going to go ahead and cancel the two h's. Now that we've canceled the h's, we're left with 2x minus 6. So we can say that f prime of x is equal to 2x minus 6. And now we want to evaluate this derivative at 2. F prime of 2 is equal to 2 times 2 minus 6. And 4 minus 6 leaves us with negative 2. So at this point, at the value x is equal to 2, our slope of our tangent line is equal to negative 2. And we found that by taking the general derivative and then plugging 2 in afterwards. Now I want to look at the same problem, but in this case we're going to look at taking the derivative at a specific place. So now we're going to use the same formula, the limit f prime of x is equal to the limit as h goes to 0 of f of x plus h. Now when you do it at a specific point, instead of writing x plus h in, we're going to actually put 2 in for all the x values. So we're going to have 2 plus h squared minus 6 times 2 plus h minus the function, and remember it's the function with 2 in place, so we're going to have 2 squared minus 6 times 2 all divided by h. And now we're going to simplify. So 2 plus h squared, we have the limit as h goes to 0. 2 plus h squared is 4 plus 4h plus h squared minus 12 minus 6h minus 2 squared, which is minus 4, and then plus 12, all divided by h. And again, I'm going to go through and cancel all the terms that I can. So here we have a positive 12 and a negative 12, so we can cancel them. Positive 12, negative 12. And we have a negative 4 and a positive 4. And now I'm going to do the same steps that I did last time. I'm going to factor out an h across the top. So the next step, we're going to have the limit as h goes to 0 of h times 4 plus h minus 6 divided by h, and then we're going to cancel our h's, and then we're going to evaluate the limit as h goes to 0. And as h goes to 0, what we're left with is 4 minus 6, which is equal to negative 2. The same answer we got on the last problem. It's that we did two different methods. So if you're ever looking for the slope of the tangent line at one specific point, you can use the second method we went through. Now if you're looking for a general derivative so you can check it at any point, you're going to want to use the general derivative like we did in the first example.